and 1966. He has been with the famous Institute for Problems of Information Transmission for many years, and in 91 or 93, I think it was 93, he moved to Sweden, or was it?
In 91.
91, he went to Lund, University of Lund, where he's been since then. And as of last year, he has been visiting at the University of Notre Dame. Have had the pleasure of knowing Dr. Zigangirov for many years, and we're just remarking that he looks exactly the same as he did about 20 years ago. And so you might interpret that he already looked old at the time, but actually it's the opposite, that he looks as young as he did then. So he'll talk to us today about iteratively decodable codes, both log and convolutional.
Okay.
And so it's the second time Kamil is visiting us. Last time was 15 years ago, and he looked exactly the same at that time. So, Kamil.
15 years ago, you look exactly like now. Okay, thank you, Tanya. So I will talk about iteratively decodable code. This is actually, I included many results which was received with some different people, and also some from presentation by Daniel Castello, professor of Notre Dame University, which he made, it's a joint presentation, which he made in some conference here. What I will talk about, what is iteratively decodable code? Actually, it's a very large class of codes, modern, I would say that it's a modern coding theory. They characterized relatively low decoding complexity. In this class, we can include the low-density codes, which was originally suggested by Gallagher. I will talk only about homogeneous or regular LDPC codes. Then I will talk about generalized LDPC code due to Kenner, different construction. I will this class include the turbo codes, but in this talk I will not talk about turbo codes. And there is also expander codes. I will talk by some way about the expander codes. So what is common for these codes? All codes have sparse parity check matrix, but not all of this code is convenient to define through the parity check matrix. For example, turbo codes is not convenient to define through the parity check matrix. They can be represented by graph, and then also they effectively operate near Shannon lecture. In this lecture, I will emphasize on convolutional version of this code. Actually, on the convolutional version of LDPC code mostly. I will give the definition of this code, and then discuss the construction of this code. Some element of the analysis. Analysis of this code is quite complicated here, and then more detail we'll discuss convolutional version of the codes here. Of the codes. Okay. So that's okay. Some results is published in some paper with my former PhD students. Some of them are published in IEEE. Some of them are published in Russian magazine Problem of Information Transmission. Проблемы передачи информации here. So, and also the last paper is still not yet published, but we are going to submit this month this paper. It's a quite large paper to the IEEE transaction on information theory. Yes. So, okay. What I will talk about? First of all, I will talk about the construction of the code. So the simple definition of the code, I will mostly define the code through the parity check matrix. What is this? So this is matrix L times N. L is a number of constraints to which satisfy this code, and N is a block length here. I will consider only binary case. Then vector and dimensional vector is called code word if product of this vector on the transposed parity check matrix is equal to 0. LDPC and GK codes, low density codes, is a code defined by matrix H having exactly G1s in each column and K1s in each row. And then code rate of the code is upper bounded by this inequality here. Lower bound by this inequality. So how to construct the code? There is, for example, a random construction of the code. So we have 3 strips, and we will put in each strip the identity matrix, which has ones along the diagonal. And then inside of each strip, we can permute the columns of this. And then we will, after such permutation, we will get different code. Here is given example of the parity check matrix. It has in each row exactly 4 ones, and in each column it has 3 ones. So the size of these matrices is 15 times 20. So block length is 20, and the transmission rate will be slightly more than 1/4. Yeah. What is sense of this? Look on the first, for example, row, which has the ones in the first position, I think in the 15th, in the or 12th, in the 17th, and the 12th position here. So it means that 4s, 12s, and so on symbols, these 4 symbols which correspond to this one, are connected with parity check equation. It means that sum of the corresponding symbol by modulo 2 is equal to 0. It means that corresponding symbol to these ones are form code word of the trivial parity check code. So they just satisfy to simple constraint, the parity check constraint. How to define the general codes here? So I will give so-called masked representation of the. I lost slide somewhere. Okay. Okay. I'm sorry, I'm lost. Have a look. Was so. Okay, then I will just describe what it is. So we have mask here, and suppose that we have code word consisting from the 12 symbols. Then we will put our mask on this code word, and then we will see that the 4th, 12th, and so on symbol in the windows here. And then the second, if we will move further, then we will get the symbols in the these windows.
This is the pattern of 1 and 0, right? This is the pattern of 1 and 0.
Yes, it's to zeros correspond the black, this, and to ones correspond windows. So if we will look the symbols on these windows, they should form the code word. In this case, they are trivial. But if you will consider more complicated codes, for example, Hamming codes, then we will get a so-called generalized code. Furthermore, we can even use nonlinear codes. Then parity check matrix doesn't work representation of this, but it's work with mask representation here. Okay.
Low density comes because the white
in this, yeah,
the white area is much less than the black area.
yeah, roughly.
Is there an upper bound before you don't call it low density anymore?
Yeah, you cannot call them low density, and I will talk about some other example when it's cannot call low density because they are not defined through the parity check matrix. But maybe there is a sense to keep this name. There is a many way of definition of this code. We can call them LDPC code because if they are representing through the parity check matrix, then it will be low density. We can call them iteratively decodable code. We can call them codes represented on graphs. And once I also call them turbo codes in wide sense. So maybe it's the best definition of the all codes, which is will include the also turbo codes and so on. But up to now, the term is we didn't find. Yeah. Okay. So now is another representation of the code. It's I call it Lego representation. You see, we have again the block length will be again 12. This is parity check matrix. It's again 15 times 20 here. But now we construct it's from permutation matrices. Permutation matrices is called square matrices, having exactly 1 1 in each column and exactly each one in the each row. So you see, this is this parity check matrix construct from 12 permutation matrices. You can choose the matrices randomly and then put this here.
So it's like a product group, right? If you get a big transformation on the original matrix, and you do it by essentially taking subgroups which are basically permutation matrices.
Yeah, probably. Yeah, this is a good definition of this. I call it Lego because it's like children playing in this. It's from different blocks.
Except the mathematics here is not children's play, never mind.
Yeah, but what is interesting that if you will, as I said, these permutation matrices are chosen randomly, and if I will look ensemble of this, it will be equivalent, asymptotically equivalent when the lengths of this go to infinity to the original Gallagher ensemble. So it will satisfy the minimum distance of the code, will be satisfied to same bound as original asymptotic if the length. So this is if you will look the if the size of this permutation matrix is m, if m go to infinity here, then in this corresponding ensemble there exists a code which satisfy to same bound, minimum distance of which satisfy to same bound as Gallagher's ensemble, more general ensemble.
So is this a density result?
Huh?
Is it a density result? In the sense that if I get, because you say if I get a very large matrices, you're going to have a lot of sub-matrices which are permutations, so basically you're proving that this is dense or in the set of codes from Gallagher.
No, this is sub-ensemble of Gallagher codes. Sub-ensemble of Gallagher codes, but having same asymptotical performances as Gallagher's code. So,
This is not the same, he's talking about the exponential dominant.
exponent.
Yeah, but suppose I take any distance, right? And the same way I have versus I say that rational numbers are close to real.
But that's not the case. What I looked at is the biggest story. I can define density to be absolute because it's an existence of world, right? I can do this on left.
Density will go to 0 in this case. If, yeah.
I can take logarithmic error, that's not a distance. It's not the problem. It's not? It's not the right way. I want to tell you that again at the end, because there's a real question at the end. The rule exponential out of bounds are good, and so any of them will come close to it and pull it down, so that's what we see. Okay, but then why do I care to do it this way? Because it's sparse. It's a smaller ensemble. The original one is sparse also.
Well, this is a smaller ensemble, maybe you can exploit the structure to draw some conclusions about the
How much more is it? Okay, let's...
No, I introduce this because in some sense, this...
You understand what I meant with the question, right? Because in the end, what I'm going to ask is whether this can be done over non-linear structures versus linear structures.
I wouldn't go on this.
Okay, I introduce this is because I will use convolutional analog of this, and this is very convenient, first of all, for analysis. It's much simpler analysis than in general case for this code from one side, and from another side they will have some practical advantage in the convolutional using this code. Now I will introduce, I call it two-dimensional spatial codes. Now you see, this is code is 2, 4. 2 is correspond to G, how many constraint, and 4 is how many symbol in it's a K, how many symbol is coming to each constraint here. So you see, it's a now square matrices having the permutation matrices as elements here. So then this is already not parity check matrix, it's just array. And if we will took the ones here and will replace all ones by symbols, code symbols, we will get two-dimensional code. So this array defined the two-dimensional code. So number of symbols here will be 5 times 16, 80 symbols. So they will be correspond to ones on this table here. And then what we can say, each 4 symbols in each row will again satisfy to some code constraint. So here, symbols here. In the same time, the 4 symbols which is coming in each column also satisfy to some constraint here. So number of the constraints is 2. And in each constraint coming 4 symbols here. We can say that each symbol satisfies to 2 constraints, one horizontal and one vertical.
What is the nature of the constraints again? What is the nature? What are you calling constraint?
Constraint, it's the 4 symbols in this case, which is on the row, should be equal to 0 by, some of them should be equal to 0 by modulo 2.
So
this is constraint.
Huh? Parity check.
Yeah, it's a parity check. And the same for table. This is a constraint here. So I can say that it's generalization of Elias product code. It was it's a sparse because Elias actually considered when they was not sparse many years ago, but now it's if you will consider the sparse, then you will get. Maybe it can call the expander code, Sash. Probably. You, huh? Yeah. Okay. Here. Okay. Then this is this, and we can generalize this is by on 3-dimensional case. Then we'll have, and this is you see, it's this code construct from 8 3-dimensional permuters. So permuter, if you will look on this cube, so and if you will take some plane, in each plane will be exactly 1, 1 here. So before in 2-dimensional case we have in permuter it's having exactly 1, 1 in each column and exactly 1, 1 in each row. Here, each plane, if you take plane here, the number of symbols here will be m times m, a possible position of the symbol is m times m symbols. But you may only distribute m ones in this cube. So it will be in each plate of the three-dimensional permuter. You will get.
Camille, there's nothing special for 3, right? I can do it for any m dimensions, right?
Yeah, it can be for a larger dimension make, but then it will be more difficult to present.
I take an n-dimensional space, I take
yes,
space,
yes, yeah, and yeah,
the permutation
yes,
and then I have
yeah. But this is also partial case of Gallagher. Not all low density chords can be represented in this three-dimensional. So it's also subclass of such chords. Okay. So now I will say that there is also these all chords can be represented by graph. Here it's tenor graph, the Petite tenor graph. So this is black notes correspond to symbol notes. It's 20 for our example, which I gave in the beginning. This is where white notes correspond to constraint. It's 15 of them. So then the edges which coming out from each symbol notes are symbolized the it's showing to which constraint the coming this particular symbol. This particular symbol, for example, coming to this constraint, and this constraint. In own turn, if we will take the parity check nodes, it will be connected with, in this case, with 4 symbol nodes. This is symbols which are coming in a corresponding constraint here. This is called a tenor graph, and this is many chords can be represented by this way. But for analysis purpose, is much more convenient to consider the tree-like graph. So now I will introduce maybe a little bit the tree representation of the chords was given already by Gallagher many years ago, but I don't know why, but then people prefer a long time used only tenor graph. And Tenor himself used actually also tree representation. But as I said, for analysis papers and tree-like representation of the code is more convenient. How we can do this? We will take one symbol arbitrary. So in this case, it's only two branches, edges coming from each, but we can imagine that it's much more here. We will call it clan head. What is we will consider for many generation. You know, it's like in Scotland clan. There is in Sicilia, in Chechnya, in Russia. So they remember who was before for many generation here. This is clan head. And then there is a G constraint with which is connected. We will call its families. So they have G families for clan head. In each family coming k-1 children or direct descendants. So this is the symbol or symbol nodes which are connected by this constraint with clan head here. So in each family we will have k-1 children. Then in own turn, each of the children of the clan head has G-1 family. It's a.
What do you mean by clan head?
It's a. We have just arbitrary symbol,
Yeah.
and we will call him clan head.
Why? Never mind. I mean, are you talking about
No, but how you will call the accedents? How it's opposite to descendants? Antecedents. Antecedents for all this. So we will make such tree. We can imagine that it's a large clan here, and they are all coming from this.
That's the root.
Yeah, but it's if you wish, you can call its root. But I prefer the genealogic representation here.
It's a grandfather or something.
Grandfather for all this. Yeah. So, and then we will have such a tree. Tree we will call tree non-degenerate if the all symbols which are here are different. The symbol which is coming to this up to at least some level. Here we will call the clan corresponding clan non-degenerate. But it's clear that if you will take sufficiently large number of generation, then they will start to repeat. But the whole theory of the LDPC code is made for the case when all of them are different. Then, if you will use the analysis of the decoding, we can assume that all decoding operations are independent because the symbols are different and the statistics which you are calculated for them is independent. Independent for them. On practice, of course, if you will look at some typical code, the generation will occur quite fast.
The fan out of these trees at each level is the same. The fan out is the same. Graph is completely regular.
Regular on the left, and the fan out is the same.
It's the same.
It's up to you what how you define it.
I'm just asking, is it for these codes the fan out the same at each level?
At each level, well, every other level, because it can be variable.
No, I understand what the fan out is. I don't understand what biregular is. So I have a graph. Is the number of branches coming out of each node the same at each level?
No, it's not.
It's not.
But do you understand the relation of the left graph and the right graph?
Yes, I do.
So then if the degree on the left is different from that on the right, then it's every other level that's the same fan out.
Okay, what about the depth?
The depths
The
you,
number of decoding rounds.
yeah.
If I start on any branch up there and I go, is it the same everywhere?
Yes. Yes.
Yeah.
Thank you.
Okay. Okay. So, it's, as I said, the important for analysis is assumption that all the symbols are inside of this clan is different here, and then if the two symbols will be, if we will meet the two symbols which are the same, for example this and this, then the graph will have cycle here, and the purpose of the construction to construct the graph such that the cycle would have the largest possible length. It's called Gish of the graph. The goal is to construct the code such that the Gish would be as maximal as possible. So now I will just give the definition of this. So we consider the clan for different symbols of this, and clan is called H sub 0 non-degenerate if nodes of the clan up to this generation correspond to different symbols, and it will be degenerate if on the next generation it will be they will meet already same symbols here. And then code call is L sub 0 non-degenerate if all the clans is L sub 0 non-degenerate. So we have not only one, not only for each particular, for some symbols should be non-degenerate, but also we shouldn't have the clans with small cycles. This is the goal how we can construct this. And Gallagher gave the lower bound for L0. This is actually connected with number of independent iteration in the decoding. And he gave, this is bound is quite simple. Upper bound, you just will count how many symbols, and then the symbols on each level, and it's you will get then this bound here. So I will only notice that this is proportional to logarithm of block length of the code here. And then this is upper bound. Gallagher also gives the lower bound here by suggesting of some particular constructed procedure or constructing of the parity check matrix of the code. He can show that this is L sub 0 is lower bound by same coefficient but by same value but divided by 2 times worse the lower bound for here. We used here a little bit different approach. We construct the code randomly by choosing here, but then we can prove the next theorem. But in this case, if we will choose L sub 0 like this, where epsilon is arbitrary number between the 0 and 1/2 here, then we can say that there exists n sub 0 such that for any n larger than n sub 0, the probability that some particular clan in randomly selected code of length n is L sub L non-degenerate where L is larger, less than L0. This probability is less than epsilon. It means that, roughly speaking, if we will construct the code randomly, then the number of the fraction of the clans, bad clans having short lengths, fraction of these clans is less than epsilon. So if n go to infinity, then we can actually all the time choose less and less epsilon, and we can make the fraction of the bad clans as small as possible. But still, we will have some amount of bad clans. It means that corresponding symbols will have in the decoding relatively large probability of error. Decoding probability that they will be decoded erroneously. How to handle this problem? So we assume that we can expurgate this symbol. What it means? We have many symbols, and some of them correspond to bad clans, clans with short cycles here. The fraction of these clans is small, as I said. Then we can prescribe to this symbol some fixed value, for example 0, and not transmit them over the channel. Here it means that expurgate somehow these symbols. Then the real rate of the transmission will be slightly less. It will be less on the value of the order epsilon here, but after that we will have only good clans, good symbols which all symbols will satisfy to this to not having the short cycles here. Now, using this approach, I will describe the methods of the analysis. This is important representation was. I will start. Yeah, I will maybe several times come back to this figure, but first of all, I will describe how we will decode in the case if we are using the code is used in erasure channel. So we transmit the binary symbols to the channel, and some of the symbols was erased with probability p, for example, here. Okay. Then we received symbols, and then we would like to, using the code connection, here we would like to reconstruct these symbols here. So it's clearly, this is we have symbol on the tree, and we assume that tree is non-degenerate. All symbols are different here. So this is symbol, some of these symbols are erased, some are not. So consider, for example, this symbol. Suppose that this symbol is erased here. So in which case it can be reconstructed, if it's erased. It can be reconstructed if, for example, all symbols from this family are not erased. Since they are satisfied to parity-check equations, so in this case, we know which symbol was transmitted here. And so on. And this symbol, for example, will not be reconstructed in the case if it's erased, first of all, and in all this family, at least one symbol was erased. Then it cannot be reconstructed here. Now, this is well known and described in literature how to decode this symbol. I gave its example because then will be simpler to me describe the decoding in the case and analysis in the case of additive white Gaussian noise channel here. So this is x sub I, it's probability of the erasure of the symbol. Stopped. Саша. Okay.
That is weak.
Weak. Oh, okay. Sasha, battery problem. Okay, I will use now the pen here. Okay, this is we are moving from down on the tree. This is, we are saying that this is last level, L sub 0 level here, L sub 0's generation. Okay. No, it's okay.
It's trying to look behind your result.
Okay, so this is first iteration, second iteration, and so on. And I would like to know the probability of erasure after ice iteration. So it's on the ice generation from the, if you will count from down here. So this is probability of erasure after ice iteration. This is connected with probability of erasure of symbol in the previous iteration here, x sub I minus 1. And then if you will just formally to write this probability, it will be satisfied to this. So if we have probability on the previous level of the erasure symbol, P is probability of erasure for each symbol from in the channel, then we'll get probability of erasure on the next level here. Okay, and then this is this curve here, and this is diagonal. This is we have two axes, it's x and y. This is a function y equal to f from x, and then if we will start in some point, for example, here the probability it should be x starting from point P here. Then after each iteration we will have the probability which is given on this x. Here we have such kind of representation here. So this is give exact probability after the ice iteration. But to study convergence to 0, x sub I after many iterations here, it is convenient introduce majorant function. So from this function we can get upper bound for this function fx, which is given more simple looks. It looks like this here. This is we call majorant function, and it will be given on the next slide. So this is original function fx, And then here we have majorant function here, which looks like this. So we, in principle, for analysis, we will get more pessimistic analysis if we will use instead of the majorant function, instead of real function fx, majorant function f from x at. It's given here. But in this case, in this region, for example, here, we cannot use, it's not will, if we will take point here in this and we'll use majorant function, it will not converge to 0. Okay. Okay. This is we can do only in the region starting from this erasure probability. This value we will call the breakout value. It means that if somehow the probability of erasure reached the breakout value, then after that it starts. You may use the majorant function, and the probability of erasure will converge to 0 with number of iteration of following the iteration. And how it will converge to 0 depends from the majorant function. In our case, it can be or linearly or exponentially decrease from I, or double exponentially. If G is equal to 2, each symbol of the low density code is coming in two parity check equations, then it will be just exponential decreasing with number of iterations. But if G is larger than 3, then it will be double exponential decreasing here. So, and this is connected with analysis of block and bit error probability. So now I can talk very shortly, because I'm a bit limited, what will be in the case of the identified Gaussian noise channel here. In this case, we have to calculate log likelihood ratio for each symbol. This is log likelihood ratio for symbol V sub m here on the tree. Here. Then it's to calculate this log likelihood ratio, we should know intrinsic information. This depends just from the symbol which received on the channel through the channel R sub m, the corresponding symbol received through the channel here, and intrinsic information. This is extrinsic information. This is log likelihood ratio of all children of this particular symbol here. So if then extrinsic information for each family can be calculated by using this formula. It's quite complicated function, tangents hyperbolic. It's a product of tangents hyperbolic, where it's from the corresponding log likelihood ratios here on the previous level. So very complicated function. And then in principle, knowing the distribution of these children, of log likelihood ratio of children, we can find the distribution of the next level of iteration for the father of the family here. And so moving on the tree from down to up, we can calculate the distribution on each level, and this is called density evolution calculation here. So, but itself, density evolution does not permit to give any conclusion from this. So you have to, they're usually calculated numerically by using computer here. But what we can do for theory, how to analyze this. This is description what we will do in theory. So if we if this is probability density function of log likelihood ratio of symbol Vm after is decoding iteration, then we can calculate Bhattacharya parameter of this. So it's actually, we have two hypothesis testing problem. We know how to distribute it, the log likelihood ratio for them, and we can calculate the Bhattacharya parameter. This is Bhattacharya parameter of the log likelihood ratio after the is iteration. Yes, and we have two hypotheses because the symbol can be or 0 or 1 here. And then we can calculate also Bhattacharya parameter for intrinsic information. And then we will get, by, as I said, by manipulation with intrinsic information, we can get the inequality which connect the Bhattacharya parameter on the is after is iteration with Bhattacharya parameter on the previous level of iteration. So this is inequality here. And you can see that this inequality very similar to the inequality which was considered in the case of erasure channel. Except that instead of erasure probability, we have now Bhattacharya parameters here. And except instead of a probability of erasure in the channel, we have intrinsic information A. And otherwise, it's absolutely the same inequality here. And then now we can look if Bhattacharya parameter of the intrinsic of the log likelihood ratio is reach some value of which called breakout value, and this is actually root of such equation here, then it will decrease will go to 0 with number of iteration or exponentially or double exponentially, exactly by same way as in case of erasure channel here. And then we will get interesting result. If we considering the LDPC code with G equal to, where each symbol is coming only in two parity check equations here, then we will get that bit error probability go to 0 and go to infinity if signal to noise ratio is larger than this. But if but the block error probability that at least one of the symbol in the block will be decoded incorrectly, will go to 0 only if the signal to noise ratio is larger than three times this threshold. So we have different values for bit and block error probability. For the case of when G equal to 3, the result is much better. In this case, both bit error and block error probability go to 0 if during the this is density evolution, the Bhattacharya parameter reached the breakout value of this. So breakout value for the case of for this case is analytically given by here. You can see that breakout value depends from A. This is Bhattacharya parameter for the intrinsic information, depends from G and depends from K. So it's for each value. For each code you can easily, and for each channel you can calculate this breakout value. And then by using computer, by using density evolution, you just will look. You will calculate this function density for, in each case, phi sub 0 and phi sub 1. And you can look if during this evolution Bhattacharya parameter reached the breakout value, then you may not analyze any longer the code. We know that if block ranks is go to infinity, then both bit error probability and block error probability is go to 0. Okay, now I will come to the convolutional codes. This is maybe most interesting from practical point of view, the part of this. So for analysis of these convolutional codes, we use these methods which I described here. The specific of all this theory that not many results can be received analytically. It's in contrast to result of old classical coding theory. Many results you can receive only by combining the theoretical method and with computational method. So here is definition of the convolutional codes. It can be defined through the parity check matrix. Transposed parity check matrix is called the syndrome former here. So this is we have string on the diagonal. Outside of the diagonal, all the symbols are zeros, and here we have only inside of the string we have non-zero elements here. So, and each element of this syndrome former are in own tune is some kind of matrices here. And the important parameter is the syndrome former memory. It's how many of such terms we have, non-zero terms we have in each row here. So it starts from 0 up to the m sub s, and m sub s called the syndrome former memory here. Okay, and then by as analogously to the block code case, we can introduce LDPC convolutional codes. This is again the codes which defined by syndrome former, having mostly zeros but very few ones on each. But the density of the ones is very small here for this part check matrix. So analogy. So how to construct this code? So we used quite. This is in our old paper which was published in '99. How to construct the syndrome former for the convolutional codes. We first of all construct the transposed parity check matrix of LDPC code. You see, this is matrix. It's having size 2 to 1, the ratio of sizes, having 2 ones in each row and 4 ones in each column. It's actually defined 2 4 block LDPC block codes here. Now we cut this and we replace this part here, right up this. So we still will have 2 ones in each row here. But we would like to construct code with parameter g and 6, g equal to 3. Then we will add here to this matrices 2 ones on the left sides. Now we will have 3 ones in each row. And then we will periodically repeat this fragment here, and we will get the syndrome, periodical syndrome former of the code. You can see that in each row we have now 3 ones, in each column we have 6 ones. And this parity, and this syndrome former will define periodical convolutional LDPC convolutional code. So, this code can be also described by graph, but it's specific graph. So all symbols are connected only inside of syndrome former memory here, and then also its graph has infinitely many nodes. It has special structure because of memory, and this is time index of symbol associated with nodes. Here. So then we can introduce window decoding. So in contrast, number of nodes is infinite, but we can each time operate only inside of some window here. We can make the corresponding, the decoding only inside of window and then moving the window here. So window size is connected with number of iteration and with syndrome former memory. And it's a product. Yes. And usually it's working like this, the decoding. It's called pipeline decoding, and it also was introduced in this old paper here. So how it's moving? So we have processors, and they are moving around along the symbols in this direction. So this is symbols received through the channel, and after the on the output, the first processor calculate some log likelihood ratios, will give it to the second processor give to the next processor, and actually it's coming to the ICE processor, and he will give the on the output of this processor we already have decoded symbols here. Okay, it can be produced in parallel here. Then, so I will skip a slide which is saying about the complexity. It's showing that complexity of this decoding is less than for block codes. And what is result of here? This is result of simulation. So we have considered the case when syndrome former memory is 2000 for convolutional codes and equivalent block codes. And this is probability of error, bit error probability here, and this is signal to noise ratio in dB. You can see that this is essentially better, so you can get the much better result here. Then, if it can be say that it's not honest comparison, because in one case it's operate in large window here, but the number of symbols which is really is involved in the decoding in the convolutional codes is much larger than in this. So okay, we make favorable comparison when the number of symbols which is participate in the decoding is the same. So we considering the convolutional codes with such a memory 2000, and then block code with block length approximately 20,000. It's in this, and number of iteration in this case was 50. So the number of symbols which were involved in the decoding is actually in this case was equal to this. And even in this case, we still get much better performances for convolutional codes than for block code. So now, since the time is limited, maybe I will look on the explanation why is convolutional codes are better than block code. Just
what would be the code ratio? The code ratio of those convolutional codes?
Convolutional codes are have better, less bit error probability.
What's the code rate for that code?
It's 1/2. In all parameters was the same. I consider only rate 1/2 code. This is again the Lego construction of the codes, but in this case it's convolutional codes. This is a syndrome former, and each square here correspond to the permutation matrices. So we put permutation matrix, then we will have here 2 ones in this column, and in this row we will have 3 ones here. Then we have here already 4 ones in each column, and still 3 ones in each row. Then after that we will have in each column we will have 6 ones here. So it will correspond actually 3, 6 convolutional codes here. So you notice that symbols from these blocks, we put here the first, this interval correspond to information symbol. This is input information symbols of the convolutional encoder. And this interval correspond to the parity check symbol. So the number of information symbol is equal to number of parity check symbol. They're the same. And this is defined rate 1/2 code here. But notice that here, that these symbols, first block, let's say, coming in the parity check equation, which is have only 2 symbols. Here, it's coming to parity check equations, which have 4 symbols. And this is coming to parity check equation, which have 6 symbols. And after that, all the symbols will come in parity check equation. All will have 6 symbol in each parity check equations. So if we will make the tenor graph, then you can see this is symbol of the first level. So, and this is parity check equation of the first level. So in each parity check equations here, coming only 2 symbols here. Here in this parity check equations coming 4 symbols. And then starting from this is in each parity check equation coming 6 symbols. Then you can see that symbol of this level protected much better because they're coming in good parity check equation than other symbols. If you will look on the corresponding block codes, then each symbol will become in the parity check equation, which contain 6 symbols here. Okay, then we can construct the 3-line graph. Then you can see that symbols of the first level coming in 3 parity check equation, and one of them is has only 1 child in this family. In this four child, totally 3 child, and in this 5 child. On the symbols of the second level, you will have here 3 and then 5 and 5 here. And then later, all the symbols, symbols will come in parity check equations, which contain 5 symbols here. And of course, because of this, the symbol of the first level can be decoded much more reliable here. So we checked this as for, unfortunately, we did it's only for up to now only for erasure channel, but still result is quite interesting, and we quite sure that we will get analogously result for additive white noise Gaussian noise channel. And this is results of our analysis. We used the analysis method of analysis which I described earlier here. So this is 3.6 code here. We use termination of the code for convolutional to make the comparison reasonable with block codes. And because of termination, code rate was not 1/2 but almost 1/2. This is in convolutional case the rate. So and then we will get that limit. This is the probability of the erasure in the channel, which for if the probability of erasure in the channel is less than this p convolutional, then we can, by using the sufficiently large code, we can get the erasure probability for all symbol as close to 0 as we need here. So the limit for this case, for convolutional codes, was this 0.488. It means that we can transmit in the channel where erasure probability is given by this. For analogously block code 3.6, the probability of erasure in the channel or threshold in the channel is equal to 0.429 here, essentially less than here. So, and Shannon limit for the rate 1/2 code in erasure channel is just 0.5 here. So this is much closer to Shannon limit than here. If we will use the code 4.8, it's more symbol, more parity check equation in which coming each symbol and more symbol in each code, then we will get in convolutional case 497 and in block case 3.383, even worse than for 3.6 code. The result for the 5.10 code is even more remarkable. So we almost came to Shannon limit with convolutional code, but in the same time for block code case is the worse. So should I stop or just make, because I would like to, I was planning to say about so-called braided code, but I don't know what about time. No. Okay, I will just. Okay, so, but I will just describe maybe sparsely braided code. What is this? Okay, so. So this is how looks the braided code, sparsely braided code. It's also our invention. So you have this is windows. In each window there is a symbol here. So if you will put, and then if you will look the symbols horizontally, you can. This is all symbol which is coming in each horizontal row. Form code. In this case, it's maybe parity check code, but it can be more complicated also. And actually, we have considered the case when each row defined in each row correspond to one of the Hamming codes. And the same in if you will look vertical symbols. So this is also from the code, some code blocks. And so you can use iteratively decoding by this way. You considering these symbols and correct or change some of these symbols by using the code connection inside of this code. Then you are going like this, like this, like this. And after that, this was going horizontal, the processor. Then there is a vertical processor which is going like this and also corrected the symbols here. So then, if we will look, I will just show the result of the simulation for this code. So this is result of simulation for different code. So you can see this is the code. This is case correspond to case when we all the curve correspond to the case when we used Hamming component codes 1511 here in this case, and the resulting code in this case of the braided code was 7/15. Practically it's 1/2 code, and then we considered the different memory of the code. Memory was equal to 105 and 4004 in this case. So you see the code is it's much better performances that are known in the block codes, and for relatively small memory, even 105, the code behave very good. Its probability of bit error probability can be done quite close to 0. Even signal to noise ratio in the channel is less than 1 dB. And in the case when we used memory 4000 code, it's practically behavior saying has waterfall behavior here, this parameter. So just now I came to a conclusion. Unfortunately, I skipped some parts of this. So the conclusion is that we have generally a conclusion is that convolutional cores are better than block codes. But up to now, all people are not only using but even considering the block codes. And now there is several places where the people started interested by convolutional codes. Before it was in Lund University, now it's in Notre University, and Agere company is now studying the possibility to apply the convolutional version of the code to the memory, to the storage problem, to the coding in the storage device here. So, but the code actually is quite perspective, but they're more complicated for understanding. Maybe it's a reason why they're not using on here, but we hope that in the future they will be used. Okay, thank you.
Thank you.
A question? What is the time performance of the decoding for block coding and convolution coding?
This is a complicated question actually, and we presented the paper on the conference will be next month in Italy, and will be Castello is invited lecturer on this, and he will talk about. It's on the Capri. I know on the place. Okay, yeah, and so he will talk quite a lot about complexity, timing, and so on. So there is some. It's quite difficult to compare this code. In some cases, the delay of the decoding in convolutional codes is worse than in block code case. But in some case, all other performance are better. It's less complexity of the decoding, but in the same time, delay can be larger for the convolutional code for this. This is in the case if your processor is very fast working. It's it's much faster than the rate of the information which is coming. But if the rate is relatively small, relatively large in comparison with this, then the convolutional codes are definitely better, even in the sense of timing.
One other question. Now, the parameters here would be arbitrary, the J and the K.
Yes.
And so, where is the nature of the boundary of low density parity checkpoints? What makes them low? I mean, these results seem to be for any parameter. So, what is low, and why is low important?
Yeah, actually, in the beginning, it was defined by, I would say, mathematically oriented scientist Gallagher. In his sense, he is considering the codes when the block lengths go to infinity, and then the density go to 0. But in this case, I don't know. It's quite difficult. You cannot say qualitatively when it's low, when it's high.
In the asymptotic results you get, you don't require that.
No. In asymptotical result, we require that it should go to 0.
The density.
Density, yes.
Okay.
Density should go to 0.
So in that sense.
Yeah, in this it's low density. But on the practice, of course, it's always non-zero. But it should be somehow close to 0.
What
was the block length of block codes that you used for simulation? Length of block codes.
In which case?
For the simulation, where you showed the rates, that the rate falls for block codes with density. The little table where we compared convolutional codes and block codes.
Where the
Ah.
were getting worse and worse.
Okay.
What was the block length for the operation?
This one.
Yeah.
So the rate 1/2.
Right. But the
So no, the convolutional it's 0.499. It's probably, I don't know, 1,000 blocks or something like that.
Block size of the other side.
So
The last one.
if you will not use the termination, then it will be 1/2. If you use termination, then you lost about 1,000.
What was the block length? It was a block length.
No, for you mean the
The last one. When you say it goes worse, did you keep the block length the same or you change it or what?
yeah, of course, block length is no. Actually, we used. It's a little bit more complicated. Do I have? So maybe I will show. I will answer on this question. Just a second. I need the. No, I will show on the slide. It's better. I will use because time was this. Let's see. So I have considered this case. So we considered this case. So what we assume, the number of blocks was fixed here, but we have studied this asymptotically when the size of this permutation matrices go to infinity. So the block length, if you wish, is equal to the number of this quality check matrix times parameter which is go to infinity. Yeah. So it's in some sense it's a asymptotic result. In the block 1/2 code,